Welcome to another video on division of fractions. Now there's another video already where I share some of the work we had done previously with dividing fractions, but this is a different view that came up as a result of a Saturday workshop. And I'd like to focus you on the situation dealing with the dog food. So the story was, I know it's a silly story, but the silly story was, my giant bag of dog food had 28 pounds of dog food in it, and I observe, because I'm a mathematician, that it takes 92 3/4 scoops of dog food to empty out the bag, and I have to go buy more dog food. But the question is, how much dog food in terms of pounds, how many pounds of dog food is in each of those scoops? So to answer that question, one might think this way. Imagine using this line segment to represent the 92 3/4 scoops of dog food. And imagine cutting that segment up into 92 3/4 individual sections. Now it's relatively easier to think about cutting it up into 92 individual sections, but what we have to imagine is we have 92 scoops, so in 92 individual sections, and then we have 3/4 of a section. So I'm not going to literally do that, but imagine I've done that. So the question is, how much dog food, or how am I to think about any one of those individual segments? So my question is here, if I cut the scoops line segment up into, and I'm thinking about cutting it up into 92 3/4 individual pieces, then each one of those little individual pieces would be 92 3/4 copies of the total number of scoops. So 92 3/4 copies of the total number of scoops. Now, if I think about that, if I cut that up into, that's an individual piece, there's 1, 2, 3, 4, 5, there's 92 of those, and then a 3/4 of a scoop. Each one of those individual sections right there represents just one scoop. Now that thinking about cutting and copying like we've done with fractions before is, I think, essential to making sense ultimately of dividing of fractions. Now, we do the same thing with the number of pounds. So what I'm thinking is, every time I put that cup into the bag and fill it up with a scoop of dog food, there's 92 3/4 of those scoops before I empty the bag. So to keep things in proportion, I have to think about cutting the 28 pounds into 92 3/4 individual sections. So this is 92 3/4 of the 28 pounds. So that's the next part of this thing, to keep the situation in proportion. Cut that pounds line segment into also 92 3/4 pieces to keep it in proportion. Each piece therefore represents, again, 92 3/4 copies of the total number of pounds of dog food. Or now, since I cut that up into that many pieces, here's what we might see. We're taking those 28 pounds and we're partitioning it, cutting it up into 92 3/4 individual pieces. And so each one of those sections is, take those 28 pounds and divide it into 92 3/4 individual pieces. So from our thinking here of cutting and to keep the situation in proportion, what we end up with is each one of those individual sections here represents 92 3/4 of the 28 pounds, or we think about taking the 28 pounds and dividing it by the 92 3/4 individual sections. But that brings us to this then. So we have 28 divided up into 92 3/4 individual sections. And that's perfectly legitimate. That's a result to, or that's an answer to the question, how much dog food is in each scoop? So there's 28 pounds of dog food in total. There's 92 3/4 scoops in total. So there's 92 3/4 pounds per scoop. But that's just not a real convenient response. So we might want to work to make more sense of it and to write it in a way that maybe is more convenient. So here's one thing. Now as I do this, I just want to keep in mind, have you keep in mind that in my mind, our students are working through this. I'm not standing at the board teaching this, telling the students how to do this. I'm giving them a problem to solve. I've certainly laid out some of the kind of structure they're thinking, but I'm really letting them work and discuss and share and try to figure out a way to maybe massage this into a more convenient result. Now, at this stage, if you're working on dividing of fractions, students might have a way of thinking about 92 full scoops and then 3/4 of a scoop, and they might know now we can rewrite that as an improper fraction, and I believe it comes out to be 371/4 scoops is equivalent to 92 3/4. So now we can get it down to that. Maybe they take that mixed number, write it as an improper fraction. So now we've got 28 pounds per 371/4 scoops. Now, if you think back to how we've been thinking about fractions, this 371/4 means you have 371 copies of, or multiply, you have 371 copies of 1/4. That's what 371/4 means. Take a whole something, cut it up into 4 equal parts, and then copy that 371 times. 371 copies of 1/4. 371 1/4. 371/4. So if we think about it that way, then students might maybe think about division this way. So what we might think about here is 371 quarter scoops is what that really means. So suppose instead of 371 quarter scoops, you wanted to know how many full scoops. Well, to bring this to full scoops, you would multiply those quarter scoops by 4. Scale it up by a factor of 4. And then to keep things in proportion, if you scale up the number of scoops by a factor of 4, you'd also have to scale up the number of pounds by a factor of 4. So 371 quarter scoops times 4 will bring me up to 371 full scoops. And then scale up your 28-pound dog food bag. 28 pounds times 4 copies of that is 112 pounds. So what we end up with is 112 pounds per 371 scoops. Now, students might not think that's so convenient either. I mean, that's kind of a messy fraction. So at this point, we want some flexibility, we want some fluency, we want some multiple representations. And so certainly students could write this as a decimal. So if you want to take 112 and divide it by 371 and get the number of pounds in a particular scoop, that would be great. But here it is as just a simple fraction. 112 371sts is the amount of pounds of dog food in 1 scoop. So at this stage, in my mind, what I'm thinking about is students are given problems to solve. Dog food problems. You saw from the workshop there was something about making cookies, there was something about blending coffees together. You can probably think of other scenarios where division would come up. But at this stage, I don't have an algorithm that I'm hoping that I'm going to give them to use. I'm hoping that they will develop an algorithm. So far, here's just the one case. We ended up with the 28 divided by 92 3/4. I'm stripping away all the context here just to focus on the mathematics and the algorithm stage. So 28 divided by 92 3/4. We changed the mixed number to an improper fraction. We scaled the numerator and denominator up by a factor of 4, hopefully in a way that made sense. So scaling it up brought us to 112 371st, which by the way is about 3/10 of a pound of dog food in my cup. But what I'm hoping for is eventually students will start to see this pattern. Remember, math practice number 8 is about repeated reasoning. So through their reasoning, they will recognize patterns and general ideas will emerge. So maybe they'll see, hey, look, there's a 371 in the denominator now, and what we really did is we multiplied the 28 by 4. Well, we give them another problem to solve. And again, I'm just trying to come up with problems that might be interesting, at least personally. So this one is relatively real in my life. If I needed 2/3 cups of flour to make my cookies, but I could only find the quarter cup measuring cup in my drawer, then my question would be, how many 1/4 cups would I need in order to get my 2/3 cups of flour? And if it's how many copies of 1/4 are in 2/3, that's a division problem. So I want to take those 2/3 and divide by 1/4. How many 1/4 cups are in 2/3 cups? So again, at this stage, I'm not really thinking about that there has to be an algorithm that the kids know. I want them to think and reason and problem solve. And so what they might do here is think, well, these are quarter cups. Well, what if I scaled that up by a factor of 4? 4 quarter cups makes a whole cup. But to keep things in proportion, if for every, if I want to know how many quarter cups are in 2/3 cups, well then how many full cups would be in 4 times as many 2/3 cups? So now we scale things up. 1/4 times 4. 4 copies of 1/4 of a cup is a whole cup. 2/3, or I could think of it this way, 4 copies of 2/3. 2, 4, 6, 8 thirds. So there's 8 thirds in 1 full cup, or we could just say 8 thirds. So I would have to take 8 thirds, or what is that? 2 and 2/3. I would have to use my quarter cup, 1 full quarter cup, 2 full quarter cups, and then 2/3 of a quarter cup would equate to my 2/3 of a cup. But again, once again, what I'm hoping is going to emerge out of these activities is students will start to see a pattern. That 2/3 divided by 4, what ends up really happening is we multiply by 4/1 to get the 8 thirds. Students are going to eventually, after repeated reasoning, come to see that pattern. So we can even move beyond context. Not everything has to have a story behind it. So maybe eventually you're working and you just want students to think about 7/11 divided by 3/5. That is, how many copies of 3/5 are in 7/11? And so maybe by now this might have been after days or several activities, several times students have been working through this, and now they're just thinking, how might I think this through? Well, maybe we want to scale up the 3/5 by a full factor of 5. And maybe we want to then, well, we would want to then, to keep things in proportion, scale this up by a factor of 5. Notice the keeping things in proportion would be a foundation that we'd have to establish here. So we scale these fractions up by a factor of 5. So 3/5, 3, 6, 9, 12, 15 would be 5 copies of 3/5. That would be 15/5, otherwise known as 3. And then in the numerator, 7/11, 5 copies of 7/11. 7, 14, 21, etc. We'd end up with 35/11, which doesn't simplify nearly as nicely, but there's nothing wrong with 35/11. So first, we scale up maybe by a factor of 5, and we get 35/11 divided by 3. So how many 3/5 are in 7/11 is equivalent to saying how many copies of 3 are in 35/11. So then students might, again, keeping this idea of them thinking and reasoning and problem solving, and of course you as the teacher are doing your thing, running around the room and interjecting, asking questions, pushing and shoving them down this road. But here's what might happen next. So instead of thinking about how many copies of 3 are in 35/11, maybe we want to scale things down and think about how many copies of 1. So let's take 1/3 of 3. Taking 1/3 of 3 will get me down to 1. But to keep things in proportion, we'll have to also take 1/3 of 35/11. Now, if you're dividing fractions, you've already been through the unit on multiplication of fractions, and so we're going to assume that that algorithm is well understood. So 1/3 of 35/11 would be 35 33rds. And so really what we have here is 35 33rds. So can you imagine now, over time, students are working through these things and they see 7/11 divided by 3/5. They see a result of 35 33rds and they think, wow, look, all I'm doing is I'm multiplying these guys and I'm multiplying these guys. And what we want is to have happen is students come up with an algorithm that says, hey, I wonder if when we divide 7/11 divided by 3/5, couldn't I just multiply by 5/3? And of course you can. Now, if a student came up with that idea, I would say, hey, let's explore that. Maybe look back at some previous problems you've done, maybe make up some new problems, maybe make up some problems that are more convenient, like 3/4 divided by 1/2. You could bust out the manipulatives and you could ask the question, how many 1/2s are in 3/4? And maybe you could imagine there's one full 1/2 in 3/4. And then there's another half of a 1/2 in 3/4. So the answer should be 1.5. Well, let's check it out. What's 3/4 divided by 1.5? Well, the theory is we could invert and multiply. And certainly 6/4, 3/2, 1.5. Wow, this thing is working. So you see, what I'm searching for here is an opportunity for students to engage in doing the mathematics, thinking, reasoning, having a foundation of what division means, having a foundation of how to keep things in proportion means, certainly multiplication of fractions, but then they come up with this idea of inverting and multiplying in a way that makes sense.